Sure. So, welcome everyone to Sasonke Bartek's monthly meet. If you're first time joining us, a very warm welcome. If you've come before, welcome back. Just a quick overview of how the evening's going to go. I'm just going to do a brief introduction of the community for newcomers. Then we're going to go over some community updates, what's been happening, and then we'll get on to Jonathan's talk. And then the end of the evening, we'll open for some breakout rooms, and these will be related to the projects and initiatives that the community is running. Cool. Also, my internet might be a little bit spotty, so if that's the case, please don't feel shy to unmute yourself and shout at me. Right, so Sasonke Bartek, what it's about. So machine learning and healthcare, I honestly believe these two things are some of the best things we have in the world to make a difference and a positive change. However, there is this technical and social chasm that exists between these two spaces. And this is, exacerbated in Africa because of many reasons, which I'm just going to summarize here as a general lack of infrastructure. And when it comes down to actually doing machine learning, there are very many steps to get this right. And I think a lot of people in the space of implementing this will tell you that before you can do anything cool with machine learning, you first have to get your data right and your entire infrastructure stack right. So there's just a lot going on there. And from a medical side, we having, Africa in general is resource constrained, which means that if you're a doctor sitting in a ward somewhere in Kenya or South Africa or Nigeria, and you're overworked and overburdened, you're gonna have very little time to delve into the depths of medical imaging or to check what your reinforcement learning agent is doing in some toy environment. So another point there is that access to relevant data is just extremely hard, where medical data has a lot of red tape around it, which is important because we, this is personal information, and we want to protect individuals the best we can. So all of these things create and exacerbate this chasm between machine learning and healthcare, and often these two groups of people don't generally chat to each other anyhow. So Sasonke Bartek as a community looks to bridge this chasm both technically and socially. So yeah, that's what we're about. That's what we're here for. So how do we do this? We go about it via community building. How do we do that? First of all, it's meetings like this, which we do almost every month, and there are talks and discussions. They vary. We've definitely got some panel discussions in the works that we're trying to organize. For more directed efforts, we have what we call research initiatives, and this is how we organize our efforts towards very particular goals for the community, and those are organized into projects. So at the moment, we have 2 research initiatives going forwards, and each of those has a single project in each one, but we could have multiple projects in an initiative. Yeah, just a little bit of admin there. Otherwise, we also offer ad hoc mentorship, advice, and ways to connect individuals in this community. So machine learning specialists and doctors and physiotherapists from both sides. Our goal is to build a community where everyone's welcome, and we can work together to forward machine learning and healthcare in Africa. So how's it going so far? Just some updates on our initiatives and projects. If you want to check out some of the stuff that we're working on, like beyond this, you can go have a look at this, our website. We've got a page there. And this community is essentially like we can call it a do-ocracy. So things get done when people have time, and there are still some things that need to get updated there. But yeah, bear with us, I guess. So the first initiative that we have going is we'd like to assess, or continuously assess, what the state of machine learning in healthcare in Africa is. So essentially a self-awareness of this community of, where are we at this point in time. This initiative has a project running at the moment. It's a bibliometric study and systematic review led by Hassim, who is a medical student and researcher in Tunisia. The goal here is to quantify and review the kind of research that's been published in this space. So if anyone wants to get involved in this, we definitely have some tasks in this code repository, and Hassim would also definitely appreciate some help writing the papers he has planned around this topic. If you want to get an idea of like what this kind of stuff entails, you can go look at Hassim's Google Scholar page. You can probably find it. So this is the initiatives page we have on our website. Just go take a look at some of the other stuff that he's published. You'll get an idea of what those kind of bibliometric reviews are about and some of the techniques that they use there. And yes, if this is something that interests you, we definitely are looking for people to get involved. And whether you're from a machine learning background or a medical background, we need individuals, balanced representation from both sides. The next initiative that we're running is privacy preserving AI for African health data sets. The project that we have there is just to make an initial data set available. Our lead on that is Archie Erkel, and she's busy doing her PhD in federated learning, which is a form of privacy preserving AI through MIT. So we've got some really awesome people working on these projects, and if you guys want to get involved, please do. The goal here is essentially to make African health data sets more accessible through techniques like homomorphic encryption, federated learning, differential privacy. We've got a talk on this if you're interested to see more. That's on our website as well. If you want to get involved, we also need help with the code base, with academic paper writing, and we're also looking for anyone who has skills going through the process of ethics approval around privacy preserving AI, because once we implement these techniques, we're going to need someone who knows how to talk with ethics boards to get it through. Can you hear me? Cool. So just a very brief overview of what we intend for this particular project, because this initial data set that we want to make available. So we're looking to work with 2 competition based AI groups. So I think you guys might be familiar with Zindi, and then Fruit Punch AI is a group that got started I think in the Netherlands. They're both great groups. We're still sort of challenging them, so nothing's been finalized there just yet. But the concept is Sasonke Vadik and these competition-based groups will approach a organization that has health data, and we'll use PySift, which is a Python library for privacy-preserving AI, to make these data sets accessible for these competitions. That way, once these competitions are done, these data sets will still be available for research purposes. And the hope is then, with one successful data set being made available, we'll be able to approach that same organization to make more of that data available. And by then we'll have a template for how to go about doing this, and we'll be able to approach multiple different organizations in various parts of Africa. Cool. So just some updates on what we've been doing in terms of the growth of Sasonke. Otherwise, you might see on our site, we updated ourselves with some partnerships and support that we made official. Yeah, I think some of you went through the Cassini registration process for this seminar this evening, so they're providing us that service for free. So thanks again for that support. Really appreciate that. And then all these other great people are involved with helping Sasonke Biotech. We're also looking to partner with more like healthcare care-based partners. So this is the South African Medical Students Association. We've approached them. I'm also going to be approaching the International Federation of Medical Student Associations. And that's because I think most of our representation at these meets and in the community is very skewed towards machine learning individuals. And we'd like to try and balance that out as best we can. So if you know anyone or you are an individual that represents an organization that you think would help us bring balance to this equation, please contact me directly or reach out to the community. We've got our Discord. You can email us. All the details are on our website. Also, we'd love to have more partnerships with organizations from across all of Africa. Again, we do have representation from Nigeria, Egypt, Tunisia, Kenya, and South Africa, but that is by no means fully representative of the entire continent. So please, if you're keen to get involved, if you think of anyone or know of anyone who thinks keen to get involved, don't hesitate to reach out. Otherwise, we've got some fun talks coming up in the coming months. I don't think we'll have a talk in December, but starting again from January and February, we'll be hearing from Tim, Tinashe, and Chris Kern. Also, this community is about all you guys. So if you would like to give a talk, whether you're from a machine learning background or medical background, please don't be shy. We'd love to hear from you, whether you're from an academic background or if you want to talk about industry stuff, or if you just have any ideas that you think are really important to share with the community. All of this is welcome. Again, the recordings for previous talks are available on our websites. Please go check those out. They're all super interesting. Yeah, otherwise on with the show. I'm going to invite Jonathan to share his screen, and I'm going to shut up for now. And yeah, I hope everyone has a good time. Again, I know that speakers generally appreciate questions, so don't be shy. Cool.
Awesome. Thanks, Chris. And absolutely. Hey, everyone. I'd really appreciate questions. This, from what I understand, is an informal session. So, at any time you see something on a slide you want to, ask about, very happy for us to go on a bit of a tangent and describe things or have a fruitful discussion point. That being said, I was initially given a spec for a 10 to 20 minute talk. I see there's about 35 minutes allocated. So we'll see how long this goes. Just a little bit of context and background. So I'm a senior data scientist at Explore AI. It's a Joburg-based or Joburg and Cape Town-based data science company. We mainly consult in the UK. And I'm also a member of the Rail Lab, where I've been doing my PhD research, and that's with Prof. Benji Rosman. I am not medical. I do have a lot of medical people around me in my family. My wife's a doctor and her father's a doctor. So there's a lot of conversations around the table, but my medical knowledge only goes so deep. So be careful when asking those questions. I might just feign ignorance and not know how to respond to you. But that being said, I obviously don't know many people on this call. And so, if I'm going to try and pose this or just aim this talk at quite a neutral ground between things which are medical and machine learning related stuff. Obviously, being a machine learning researcher, I'm a bit more comfortable with machine learning concepts, but hopefully, I won't go in too deep technical anywhere, so I'll go ahead. So why are we here? I'm speaking about seeing things clearly, and what this really has relevance to is medical image processing, or in computer vision in more general terms, if we don't make it domain specific, and using hard attention and structured knowledge essentially to enable reasoning and image understanding within this format. So very quickly, what I'm going to be speaking about in this talk, I'm going to give a bit of a primer on explainable AI and its pitfalls in medical imaging. I'm going to speak about the relevance of hard attention models when it comes to explainability, and also the topic covered previously of around its context in medical imaging as well, and then how we take this further in terms of structured knowledge. This is a bit of a conceptual talk in the sense that I'm going to present a little bit of work that's been done around hard attention models within my research, but going forward with structured knowledge, this is more of a position paper or a position talk of its relevance and its importance as we go forward. So when we speak about explainability, what are we essentially talking about when it comes to AI, or more closely zoning in when we speak about computer vision? Well, first of all, it's important to know that explainable AI has been around for a very long time. It's old as the field of artificial intelligence as a general field of study itself. It's recently had this resurgence of interest, and that kind of corresponds with the rise of deep learning once again, as it has a lot of industrial interests. Obviously, we know in the medical imaging community and healthcare industry at large, a lot of deep learning techniques, because they're data driven, are very applicable. Regardless of the difficulty of us deploying these methods, there's a lot of interest in these techniques, and so kind of corresponding to this, to enable these techniques more so, we need to understand them, we need to be able to audit them, and the notion of explainability comes into this. The important thing to understand, though, is explainability as a concept is not tied down only to the the sciences, or the hard sciences in terms of computer science. We often need to think of explainability as something which is psychological. It's something that is in the humanities as a field of study. And so because of that, I think, in many senses, you often find researchers trying to, hijack the concept of explainability and not using it appropriately. And so a lot of these factors kind of come together, where computer scientists are trying to speak about explainability without a full context of what it really means in the broader context of study. And so it's a bit of academic Wild West, as I mentioned here, the fact that the term explainability is thrown around very loosely. And so the first thing that comes around where terms are conflated is we have to understand that there's a bit of a difference between the term of interpretability and explainability. When we think of something being interpretable, it's this intrinsic property of something. It's passive, internal, that allows a given model, if we speak about a machine learning model, or a given model, to explain what it's, how it's gone from an input to an output, and this mapping between the two. And when we speak about explainability, it's an active characteristic, associated with a model, where, there's a technique that's often applied in order to clarify the mapping that is done between an input and an output within one of these systems. So kind of a good way to visualize this, we can often think of like maybe an input image to a given system, and this would probably be a computer vision model. Maybe it's a convolutional neural network or something, but we have this input to the model. And often the time when we refer to something being this black box model, it's the fact that we are able to derive an outcome prediction or an inference of some sort, but the internal mechanism behind that prediction, behind that inference, is unknown to us. It's, often these are extremely hyperparameterized models, and so what actually is going in, the calculations that are taking place, are unknown to us, and so these become opaque or black box models. When we speak about something interpretable, we have the model explicit before us, something like a linear regression model, where we know that there's an input, there are direct mappings of maybe the input features to this model and the coefficients of that model to the output. And so we're able to understand, this direct mapping. And then there's explainability, where the model itself is still, opaque to us, it's still black, but the intrinsic, we use active techniques in order to go, to justify or to characterize why a outcome was given. So in this case, it might be that there are halogen lights, identified, there's a concrete floor, there's machinery, and so we know this must be a factory setting, for example. Now, before we just go, interpretable models are obviously the best thing in this scenario. And if we think of medical imaging, a simple interpretable models are the sure win here. The big limitation is the fact that often interpretability, it's not mutually exclusive from complexity. And it's very easy to have a interpretable model that has so many parameters associated with it that it no longer becomes easy to justify or kind of rationalize or behind why a decision was made. So when we look at explainability then and going forward, the most typical form that we're used to in studying in machine learning systems or associated with deep learning are what are known as post hoc methods. So these are essentially explainability techniques that act upon a model following an inference being made. So the first and most common form of this, and it's often seen widely within the medical imaging community in the form of saliency maps, but is this notion of feature importance. So it's, you have a given input set of features, and we're saying, we're doing a mapping from the output straight back to the input of saying which of these was the most relevant in making a prediction. And the unfortunate thing is there's this growing body of research, from 2018, 2019 already. Kleinans and others have done research here just to show that a lot of these techniques are very fallible. They're untruthful in the mapping that they often produce, and they're extremely sensitive to input perturbations. You have another set or class of these techniques which often involve model simplification, and here you have something like LIME and its various derivatives, where we're trying to have these locally interpretable models which are saying you've got this very complex model, but we're going to generate an interpretable model on top of that that will kind of give an explanation behind what is happening in terms of the predictions being produced. And then there's also, what is more so recent and a new direction that's been undertaken, is trying to get conceptual representations of what is important. And so that's maybe saying, instead of looking at individual features, we aren't looking at a pixel level, we're maybe looking at superpixels. We're looking at more or more granular entities within our input space, within a given maybe image, for example, that helps us know what is actually important. And what's important here is both feature importance and model simplification. Feature importance happens on a per image or per data point instance, where you look at one image at a time and you try and find out what was most important. Things such as model simplification, but especially conceptual importance techniques, look at the global or an entire class in order to determine what was the most important component in a classification that was given, which gives a bit more certainty towards understanding if the model really knows what's going on, if this learner has learned appropriate classes or appropriate concepts in order to perform classification. Now, bringing this closer to healthcare, this is an article that I literally pulled today, so it was published 3 days ago. As the title shows, before going any further, I think one of the things that we have to step back and appraise is, is explainability even feasible when it comes to healthcare? And I will once again take it from the context of medical imaging. Is there any feasibility behind this? And some of the justifications made in this paper, it's an opinion piece published in Lancet, but so it's quite reputable, and it obviously there's thought behind it. One of the points the authors raise and is cited is the fact that post hoc explanations that everything that we've looked at so far must at some level be wrong, because they're an approximation to a prediction already. They cannot, it isn't the model itself that produces this, it's a technique that is applied to another learner or to another technique essentially. And so at some level they're inherently wrong because they're an approximation to why a prediction was reached. The other thing is, and we've seen this quite a lot, if you've ever had the misfortune of working on a medical imaging project or something, or, with medical data and machine learning, is you often believe your model. You think it's right. And so there's been a lot of research showing how, the explanations that machine learning models produce are very subject to cognitive bias, to us believing them or to believing an explanation that has been produced. And the last thing to really note when we speak about healthcare is to step back and ask, what are we actually wanting from our explanations? If we look at the post hoc explanations that have been given there, we often see that they're descriptive in the sense that they are trying to say, well, this is the region that was most important for a prediction to take place within an image, for example. And what they don't provide, which is the real thing that I think as a, within the medical community, when you're trying to audit or, critically look at a medical AI system, is to have some sort of normative evaluation. You want to compare it to just as you would a peer, where you're saying, I can see why it has made this decision based on these motivating factors. And so current forms of explainability don't really provide this platform for normative evaluations to take place, because they aren't giving, direct reasoning behind why something happened. It's just a description of what has occurred. So, obviously the references are quite small, and this slideshow will be available after the talk. So, if you want to see some of these references, you can go in there. That leads us, though, to another form of explainability techniques, which are often newer, and these are known as anti-hoc methods. And so what we're looking at now, these techniques that act during inference, so they're baked into the model itself. Something that you can think of here are things such as transformers, or more broadly, forms of attention within learning mechanisms. Here, this is where a subset of the input space to a model, the subset, maybe like a portion of the image is focused on in a soft manner. And I'll get to hard attention next. But essentially what we're speaking about here is, very similar to visual saliency. We're using some sort of attentional mechanism to drive what parts of the image, what parts of the input space we should be considering more deeply. Once again, though, there's a big problem that these techniques are, very vulnerable to small input perturbations that take place. One thing that I want to, jump into and speak next about, though, is hard attention. And so I'll hold the floor until we get to that point. But this is a second sort of attentional mechanism where we try and discretize the input space and very, consciously just look at a subset of our inputs based on an attentional process that takes place. And the other thing that I'm going to touch on in this talk is structured reasoning. Okay, the ability to utilize what, I'll explain in a little bit of, but is symbolic knowledge in order to make inferences, to make predictions or decisions based on additional sources of information that are used to bolster a prediction that takes place. And what we'll see is, these sorts of systems are very valuable because they lead to contrastive explanations being produced. All right, so what is hard attention? So if we can kind of step back and think of a computer vision system, something like a convolutional neural network, if any of you are familiar with that, which I know quite a few of you probably are, we as human beings don't see like computers do. We don't have a, constant resolution to our field of vision. We have, if you look at the anatomy of the eye, we've got the fovea, and, the way that the eye is structured, we have a small or a very acute part of our visual field, which has quite high resolution in terms of its input. And the rest of it, has a lower field of, resolution, essentially. And so how we see as human beings or as mammals and organisms to a large extent is this process of saccading. We, look at, as this little GIF is showing, we look at different parts of our visual field of vision in order to pick up salient or important pieces of information. And this is kind of indicated by this image on the right here, where you have a picture of a young girl's face. And what the mapping on the right here is the general sort of saccading or glimpse trajectory that takes place of where we identify certain features of importance. So regions that obviously have more points here are visited more frequently as opposed to other ones. But as we look and as we see the world around us, we tend to fixate on certain portions. And this is this notion of, saccading around and foveating, essentially the quick, rapid movements that the eye makes in order to look around a visual scene. So hard attention now is the computer analog to this natural process that we do. So considering kind of the biological motivation for us attempting to do something like hard attention, it's important to, as I've said already, understand that convolutional, we aren't convolutional neural networks. They're only account, convolutions, just kind of the biological analog to that, only accounts for a small portion of our human, visual reasoning system. And so things like eye movements, the glimpses that takes place, the saccades, they're integral for the vision we have. And it's also very important to understand that, vision is functional in the sense that, where and how we look is very much a part of the process of what we're doing. And so the images on the bottom here kind of show that you can have the same scene, and given the task, either to identify over here, and it may not be too large for you, but to kind of get a sense of what is this person doing in the image, in both of these two images, the leftmost of the pair, this is kind of where people are looking for, what is the person doing, or what action is taking place in the image, versus on the right-hand side, where are they where is the scene taking place? You'll see that there's different sorts of areas of fixation, different areas of concentration. And this shows kind of how we look in different places, or we look for different things, different visual cues or salient points in determining what is actually happening within a scene. And so, what this lends us to doing is understanding what we're looking at is important in the sense of how we look at things. It's important to understand that bridge that's made. So just kind of going back and looking at, the framework from a kind of this computer analog to hard attention, how it works. Generally in hard attention models, what we have is it's a series, depending on how it's formulated, it's a series of these, often for deep learning purposes, of neural network models. But what they really kind of take in at the moment, if you can think of the saccading that I've been describing, is you have some sort of visual input. So that could be represented by X here, and I've demonstrated this with an X-ray, and some sort of location component as well, some spatial component. And so we both have visual input and a spatial aspect, and that's describing what we're looking at and where we're looking at. And what is often occurs is, these two pieces of information are, fed into a model, and they are individually processed and then fused to kind of get this notion of a glimpse that takes place. And so we'll often have as I said, the input image. We'll have some sort of idea of, a location which is used to extract a piece or a component of the input. And this is where there's this kind of like discrete part that's extracted, this patch, and that's where the hard component of the hard attention comes in, the fact that you discretely taking a portion of your visual input, and you're also putting in the spatial information. And these are often processed, either this is a neural network here, the visual component might often be processed via a convolutional neural network or something. But these two pieces of information are taken, they're fused together, and they produce a internal state, which is a glimpse. And essentially what you have is this idea of, this glimpse information is processed to have this internal state within this model. And what it's doing is it takes this glimpse information and uses it to really decide, where am I going to look next? And what should I do based on the stuff I've seen? What sort of decisions should I make? And that's represented by two kind of output networks that are often inherent. And this process happens again and again and again, because as we know, we aren't taking just a picture with our mind, we aren't taking a single input, we're continuously processing information, and often these hard attention networks are formulated in the same way. And you can kind of ignore the nomenclature over here, just the various signs. It's to know that we're taking in visual input, spatial information, we fuse this together, and we, in a repeated process, we keep on using this information to update what we're looking at, where we're looking, and what we believe we're looking at in this repeated form. Now, why is hard attention quite desirable from a explainability point of view? one of the first things that comes out is, we currently have, of these, explainability methods, if we're looking at those post hoc methods I was speaking about earlier, or even some of the anti hoc ones, we have very limited literature in terms of how to actually objectively assess the explanations that any model produces. As that article had already highlighted, there's a notion that our explanations are inherently wrong because they're approximations, but we don't actually know how wrong they are because there's so little literature or methods of truly assessing explainability. And that's a key thing to understand. If we are trying to do assessments, they're often subjective, and this is where the human, the social sciences come in, but they're extremely rigorous to do properly and are human intensive. So what we see from something like an anti hoc method such as hard attention is those glimpse of trajectories that we form, where we're looking and how we're looking, over time. Those provide data for validation. They provide fixed, data points that we can evaluate in a rigorous manner. So, just taking a portion of research that I've done, and to illustrate this, here is a simple example. These 4 images are illustrative of this toy domain in which we have geometric shapes. In this case, it's just a single shape, a square, that is distributed around a given image. So essentially, depending on where the shape is, the square, for example, that will determine the class that this image belongs to, where you'd have 4 classes in this toy domain. If a square is in the top left, it will belong to a given class, and if it's in the bottom right, for example, it will belong to another task. Just out of passing, this is something that immediately a task for a convolutional neural network would struggle at quite a bit, just because the fact that you've got spatial pooling that takes place. So it's difficult for a model to work out, where something is spatially. It's more based on the features that are there, unless you've got some encoding scheme that you've used for your image. But what we can ask is, all right, can we, using a hard attention network or a model, can we work out which class, we're looking at, and what sort of explanations will a hard attention model give us? So what I've got over here, and I apologize for the poor resolution of the actual text at the bottom here, but what we've got is a single image over here, and we can see this process of glimpsing over 4 steps or 4 sequences. The box in, the hollow box in green over here with the red dot shows essentially where a glimpse has taken place and how this evolves over time. At the bottom, we've got a categorical distribution of what class the model believes it's seeing. So in this case, the first glimpse is the bottom right-hand corner, and we've got a pretty, there's no clear one mode essentially that's been selected for this distribution of where the model believes it's looking at. It saccades from the bottom right to the top right, and immediately we can see that the kind of confidence is either gone that this is in the top right, it hasn't updated from this glimpse yet, or it's in the top left. And it takes a glimpse further, and we see that we're looking at the top left image at this stage. And so you can see how the confidence evolves according to the glimpse sequence that's taken place. And we can see this repeated again and again, where we see quite logical glimpse trajectories being formed by a model here once it's been trained, where it's looking at the bottom right-hand corner, it'll look at the bottom left, and it knows that, basically the object is either in the top right or the top left to which the glimpse goes. And so this gives us, just from a visual perspective, as this is the model's functioning, there's no technique that we've applied to this. It's just part of the model's intrinsic functioning that we can start to see, what it's considering, and to logically appraise, or just kind of objectively appraise what is being looked for in this case. So that's a just a bit of a demonstration of a little bit of a framework here, where we're using the direction of where we're glimpsing and visualizing this along with the belief state of the model to give us a notion of, is it looking in appropriate places? Can we use these explanations to kind of reason out what is happening? And just note that this is still subjective in what I'm showing you. We can take this further. And so if we make the domain slightly harder, we can have essentially 5 different classes now, and it's not the positioning, but the actual content of the shapes that we're presenting. So here we would have, these geometric shapes: square, triangle, rhombus, rectangle, and kite. And what the model would have to do now in terms of performing a classification or classifying these different shapes into their respective classes is it would need to kind of consider important conceptual pieces of information in order for the classification to take place. So for example, here you would see that, first of all, there are common concepts amongst these classes. Things such as, the 90-degree angle over here is common to both a square or a rectangle. Each of these shapes can be perturbed and augmented in terms of rotation, translation, and its magnification. And that's true for other things like the tip of the triangle and the lower tip here of the kite, or the upper tip of the kite and a rhombus. These are common concepts across these classes, but we can also see that there are unique or essentially defining concepts that can be discovered here as well, such as the length of the rectangle. So the distance between one 90-degree angle and another one, can differentiate the rectangle from a square, or the angle formed between the two, triangles essentially involved in a kite, the larger, and the smaller one over here, or the rhombus. These are unique defining concepts. And so what we can do now is take these explanations even further and saying, if something is classified as a triangle, have the discriminative or the defining concepts actually being detected or discovered going forward. And so again, some more visual results from this process is the fact of, here we can see this glimpse trajectory again taking place for one of these shapes, where again at the bottom we've got this distribution over the classes: rectangle, kite, rhombus, triangle, square, and the glimpses that take place over a glimpse trajectory, a number of these glimpses, where we can look at a certain portion and we can see that, given from this point to this point, there's high confidence that the actual model has seen a triangle based on the information it's seen. And that kind of increases until at a certain point, it views the correct angle of the kite over here, this discriminative piece of information, and the confidence over here builds around the correct class being of a kite. So that gives us, once again, this is intrinsic or ad hoc explainability that's coming about. We're coming to understand what's going on here. And what we can do, though, is also see where failure modes occur. So we're not to believe the hard attention model whatsoever. So here we see that, there's the model really kind of gets into this failure mode where it will see a portion of this larger triangle, but it never visits any part other than the edge, this trailing edge of the shape. It doesn't go any further. And we see that the confidence mass all the time, I know you might not be able to read this, but is centered around a kite. Now, this might be a portion of a kite, but we know because it hasn't visited other portions of the shape that essentially, it hasn't learned a correct representation, or the underlying, classification of this as a kite instead of, a triangle is inappropriate. And we have objective measures. So there's research that I'm not going to show you here, where we define or we anchor conceptual points here, and we have these these objective metrics of, what proportion of these glimpses are going to conceptually relevant areas, as a way of us actually teasing out whether a model is, even if it gets the right class prediction, whether it was truly seeing salient or discriminative information to make the correct prediction. And so it enables us, when we use hard attention, the mere process of inferring has an explanative ability about it. One thing that I will caution, though, is this whole time I've been still giving a subjective explanation to you of why, these things are dating. And the fundamental problem we have with a lot of models, regardless of how they execute, is the fact that we will always have this notion of, subjectivity in interpreting the explanations that are provided. Because even if we have this model looking at the correct areas, for example, these discriminative points, the question can be asked, why did it decide to look in a certain area as opposed to another area? In this case, for this failure mode, why did it decide to just kind of view the edge and then trail off without searching for additional portions of the input space? And so this open question kind of leads us to go, are there more concrete ways that we can reason about the conclusions reached by models? And so this is the part of, the talk where we're looking at, going beyond just a pixel input, but really using two pieces of key information, and that's around structured knowledge and symbolic reasoning, in order to really enable explainability and improve the ability of image models, especially in the with relevance to the medical imaging domain, how we get further value from the predictions that are made, or the inferences, diagnoses that could be made. So importantly, I'm going to speak about a relatively new field of AI, which sees kind of the joining of the symbiotic relationship between neural or connectionist systems, so neural networks, deep learning that we're familiar with, connectionist-based approaches, and symbolic systems or symbolic approaches. And I'll explain what symbolic approaches really look at in just a moment. But this kind of fusion of these things as neural symbolic systems. The first thing that I'm going to just say is it's important to note that even at a biological level, reasoning and feature extraction occur with different parts of the human brain. So the visual cortex is not, responsible, at least in my limited knowledge, for performing higher order reasoning. That's the frontal lobe. That's a different part, and so one could say that there's an analogy to some degree of feature extraction or sensing in the environment versus reasoning within the environment that take place. The other thing to note is, if we just expose ourselves to data-driven approaches to machine learning, if we're learning purely via induction, and so we're just taking data and saying, learn any patterns that you see from this data, well, there's obviously some correct patterns that we'll see, but there's also some spurious correlations that are inherent within the data. And this is, anyone who's done some machine learning or a machine learning project will know this, where, you want your machine learning model to determine or pick up on one key salient piece of information, these salient features within the input, but there will also be tons of spurious things that it'll learn. So, for example, in my master's, I was working with chest x-rays, and you'd want the thing, you'd want your underlying model to learn of a pathology, but what ends up manifesting is it will read perhaps a label for the chest x-ray that is present instead. It will look for low-level pixel data, artifacts within low-level, low-resolution pixels, essentially, as opposed to the pathology that you're trying to do. And so, once again, if learned just purely via data, we will learn spurious correlations. There's no easy way around that. We need to therefore have some domain theory embedded within learning in order for us to be efficient and not to get these spurious correlations. And it's important to note that, within the healthcare sector, information fusion is being looked at quite closely, where we're saying there are different ways that we can maybe take different sources of information and learn from those directly, still via induction, where we're just processing this information, but maybe by giving more pieces of information, we'll learn correct mappings. So that is a form of information fusion. But what we're saying here is we have to have a level of understanding that's higher than that, where we really have a rule-based set of saying, if feature X, Y, and Z are present, this is the outcome that we'd be expecting as a classification, as maybe an inference, like a diagnosis that would be, possible based on these pieces of information. So, the other thing to say here is, if we look at the merits of the different systems we have available to us, so the fact that neural networks, deep learning, has proven to be extremely powerful as a sensing, mechanism, as this ability to process or extract features from our input. If we tie that in with the fact that we can have other systems that are able to reason over information that is present in symbols, then we have this very powerful, engine that can come out where we're able to extract information from a given input and reason over that. And again, this doesn't have to be the same thing. These can be separate components of a greater system at play. So just to speak very quickly, if I'm speaking about symbolic things, symbolic AI, this all deals with symbols or pieces of structured knowledge, essentially. So just very quickly as a bit of introduction, in the early 60s, we had essentially rule-based machine learning or rule-based AI systems, what these often relate or required or worked for were knowledge bases. And so these are repositories of what are essentially known as factual triplets, where you have a, some sort of entity, such as a person over here, like Nelson Mandela. We have a relation, such as, where they were born, where this entity, some relation of this entity, and another attending entity, which is often, referred to as a tail and a head. So you'd have Nelson Mandela was born in South Africa. And so we have two entities and a relationship between these, and knowledge bases made up these kind of very well-defined pieces of information, factual triplets. And what this could be used for when information was abstracted into this form, you suddenly have a very powerful way of being able to reason at a mathematical level, essentially, over information, over what is presented to you. So this has been, following the knowledge bases that we had originally. This was extrapolated onto a more graph type structure. And so this same knowledge base over here can be represented as a knowledge graph, where you have these entities and there's this directionality that's represented between someone like Nelson Mandela being the winner of a Nobel Prize, being mentored by Walter Sisulu, being imprisoned on Robben Island, this directionality. And we can now use more advanced techniques to mine these knowledge graphs in order to infer certain pieces of information. So again, this graph has the same process, the same contents of entities, relationships, and facts. And these facts are something like Nelson Mandela being a son of Nkosi Fani, for example, over here. When we take this to an image domain, though, we can further extract this to, from something that's just textual to contain image information as well. And so here we have something like, when we look at image symbolic reasoning, you have something like this, which is a scene graph, where we now have these entities being portions of the input image, such as the statue in the background, Nelson Mandela over here, an object they're wearing, such as a tie. And we can still have these relationships defined between them in this knowledge graph, where we are able to formulate, these relationships between entities and the relations and have these fractal triplets. And so this kind of forms the scene graph now in a visual context, where we have, the bounding boxes, which are the visual entities, the entities themselves, what they are. Is it a statue? Is it a suit? The relationships, and essentially the facts that make up, the two entities and the relationship between them. So it's really important and exciting to know that, when we speak about these symbolic systems, we have the ability, and recent research, it's really come into the fore about 3 to 4 years ago, and is actively going on, of this notion of, being able to apply structured knowledge, these forms of, almost symbolic reasoning that can take place, using things like these scene graphs that are available or can be constructed. We can use them to perform both semantic and spatial reasoning. And so in the image on the right-hand side here, a common street image, what we can do is things like spatial reasoning, where if we are able to detect multiple windows, if we have something that looks similar to it and is next to a whole bunch of things that are identical, we can spatially work out that, based on location, this is a window that we might be looking at. We can have also something semantic, such as if, we are able to detect a car and we're able to detect something within the car, there's a high likelihood that this is a person, because people drive cars. So there's this semantic notion of what is inside here. So these are all, portions or things that can be unlocked using structured knowledge. Currently, work that is done on these scene graphs that are constructed involve, these densely annotated scene graphs that are formulated. And, it's important to note that, while there's a lot of potential that comes from using these scene graphs, so doing this kind of structured knowledge, the automated process of this, automatically generating scene graphs, requires strongly supervised object detection. It's something that doesn't come naturally. And so while, it's holds a lot of potential, there are also current limitations to this process. So, what I, bringing things together in terms of what we've spoken about, we know that there's, immense power in explainability, but we need to use the right forms of, explainability methods in order to progress, in order for this to have relevance within a, medical imaging system, or at large, even trying to reason over image input for a computer model, computer vision model, or even more generally, explainability becomes very important within AI systems themselves. What we can say even further than that is it's really important, or a high level of reasoning that can come out is when we are able to take the inputs, features that we have, and to kind of have these embedded in a sort of symbolic, or at a symbolic level, because then we can perform reasoning that incorporates understandable relationships in those scene graphs that I was showing you, in the knowledge graphs that take place. It's very easy to reason out what something is in relation to something else, based on knowing that there's an entity and that there are certain relationships that exist between entities. So when we speak or look at forming knowledge-enabled AI systems, and once again, we have the example of maybe a system here that would be involved in the diagnosis or the reading of radiographs, chest X-rays. What is something that can arise here is the fact that we can use multiple components of these different ideas together in order to arrive at something. And so you can have an input image that goes through a hard attention model, and currently my research looks at extracting areas of interest from a given input scene. And these are this occurs at a concept level, where we're saying what is conceptually significant within this image scene, what is conceptually significant to extract here. And it's then taking this notion of this conceptual information and saying, can we detect this, or can we embed this within a knowledge structure? Can we put this, these important pieces of information in something like a scene graph, where we're able to work out the content, of the various concepts that have been extracted, and also their relationship to one another, if based in structured knowledge that is present. And what that allows for as well, within a knowledge-based system, is a sense of distillation that can take place, where once reasoning occurs, we're able to derive an inference, and that's quite explicit because of the reasoning process that takes place. Knowing that certain pieces of information are used explicitly within such a system in order to derive an outcome, we're able to ground our knowledge, ground the concepts that have been extracted. Once they've been reasoned over, we can distill this knowledge back into a model. And so there's a bit of a virtuous cycle, because this then helps improve the training of an underlying model that takes place. And so this is conceptually such a knowledge-enabled system that could be formed. So if we were to extrapolate this or think about this for a medical knowledge system, it's important to understand that there's a lot of potential if we were to conceptualize and go forward with such a system, and there are also drawbacks. Okay, so it's important that if we look at something like neural symbolic systems, systems that use both forms of deep learning for feature extraction, and then this idea of symbolic reasoning, this forms of structured knowledge that can be reasoned over. It's a very young field, and so because of its immaturity, there's a lot of kinks that need to be smoothed out in terms of the process of integrating visual knowledge or knowledge that has been extracted into a symbolic framework, such as a scene graph, or a some form of structured knowledge that takes place. As said, the general processes that we have at the moment of generating scene graphs that are often used for this knowledge-based reasoning is very data intensive. And so they often required strongly supervised models in order to do object detection, to extract entities, and that requires a lot of hand labeling. And once again, embedding a given visual entity, it's not trivial, or embedding an entity within a knowledge structure isn't trivial. But there's also a lot of potential, and so just looking forward, why someone might be motivated to do this. Healthcare is inherently full of structured knowledge and metadata. We have radiographs that often have quite detailed notes associated with them. We've got electronic health data. We have the fact that even in categorizing, I know from radiological data, we have mesh systems, for example, or mesh terminology, where there's an inherent structure in the data that we look at, and this is something that can be bootstrapped and utilized in order to help us embed information in a structured way. This is what I feel is a really important goal to look at, because symbolic reasoning, once again, it gives a platform now for normative assessments to be performed when we look at AI-driven decisions. So, the information that we're able to extract, because we can perform explicit reasoning now over what is extracted from a system, it gives us the ability to evaluate whether it was correct. Even further than, were the correct areas looked at? It's saying, was that information used correctly in order to infer something, in order to rationalize? And the last thing here is, when we have this interface between structured knowledge, we're obviously looking at knowledge systems, and this is where a lot of domain expertise can also be used to appraise the inferences that have been made, to look at the knowledge that is available and seeing how it can be enriched based off a model and what it's extracting in order to go forward. So as said, this is ambitions of research that I'm looking at, but it's a a very fruitful area for individuals who are interested in this type of work in terms of explainability in relation to medical imaging systems, medical systems, or healthcare systems. So just putting everything together, I know I've waffled on for quite a bit of time. Once again, the main takeaway points here: to explain something in relation to AI, it's non-trivial. We, as noted, especially in healthcare, we're probably explaining things incorrectly. And the other thing is, we need to look at, ways that we can really subjectively, or really objectively, look at what we're trying to explain. Can we get normative assessments, essentially, of the explanations that are being produced of a model, essentially? So we need these approaches that are intrinsically explanative and accessible. Hard attention is one of the ways that I've highlighted. There's the structured reasoning, and domain expertise is something that inherently is required when we are using machine learning models. So structured knowledge and symbolic reasoning provide a platform for this normative evaluation to take place, for us to learn the correct things when training a machine learning model. And that's what that symbolic AI relationship, symbolic connection, neural symbolic connection really brings about for us. So, towards the end there, I know that the talk may have gone in a number of different directions, but these are things to think about. And yeah, thanks for listening to me, and I'd love to hear any interaction, comments that you may have.
Cool. Jonathan, thank you so much. That was a fantastic talk. I feel really privileged in the fact that I've seen sort of earlier versions of this talk when you presented it previously at RailLab, and it's so nice to see some of the new research that you've done along the way. I think I saw it first when you were talking just on the glimpses and the hard attention there. I hadn't seen any of the stuff related to the structured knowledge graphs, and it's really cool to see the direction in which the research has gone. I'm just going to take a moment. If anyone wants to just use the reactions that we have available to us in Zoom to thank our speaker for the talk, the claps and whatever emojis, like now's a good time to do that. But yeah, beautifully in depth. I think that's a lot of the technical aspects are you really went into quite well. I'm quite excited to actually go over some of those again in the recording. What I'm going to do now is just try and direct some of the questions. I've got some questions of my own. I'm going to try and keep them directed at the interface of machine learning and healthcare, and like sort of try to pick your brain to see, what do you think might need to happen to see some of this research realized, to be used in the wild or in the field, and what it might take to see this stuff happening in hospitals. And I am quite glad that you touched on the increased overhead of labeling for the knowledge graphs or the scene graphs, because that was something I was going to ask you. So maybe let me put that forward as my, actually no, I'll swing back around to that. So my one comment here would be, and this is also just to the audience in general. So myself, coming from a medical background, when you're in a hospital and you're looking at an X-ray or an image or something, at the end of the day, it is the medical professional that has to make a decision on whether or not a diagnosis is there. And a lot of the even the language in this space is around computer-aided diagnosis and not necessarily like fully automatic diagnosis. So when we talk about explainability, that's a really important aspect when it comes to realizing these systems, because the medical professionals need to be able to work with them and need to be able to trust these systems, to know that this is the reason why this diagnosis was made. It was because of this particular part of the X-ray that the convolutional neural net was looking at that suggested that it's malignant. I had a question in that. What was it? So,
I can comment on what you're just saying, and it might jog something. And so definitely, I mean, I think as early the moment a radiograph was digified, and I think this was early mid 1960s, it was around 1965, when that process took place. The immediate reaction that a lot of computer scientists jumped to was, we're now going to automate this process. If we can get good descriptors. And so it was a person who was manually outlining tumors within the lung, but if we can manually do that and feed it was to a Bayesian neural network, it was basically it wasn't neural network, it was a Bayesian classifier. But if we can, do this, we're going to automate this entire process. And that was a great dream for about 5 years. And then suddenly the field really backpedaled and went, this is way too complex to think about whatsoever. And so, yeah, computer-aided diagnosis came in. And just to comment on the need for explainability, I haven't looked at the literature very recently, but I know there was a recent study in about 2012, 2013, where, this was for the reading of mammograms using computer-aided technologies, computer CAD-based mammogram and cancer detection. Basically, the finding was that the system, and this has been reported elsewhere, that the system was detrimental to the performance of clinicians, because there was either an under-reliance, but what was more pathological was an over-reliance on the inferences given by the thing. So, ultimately the medical individual would be looking at the image or the radiographic data, and they would have to make a pronouncement. This CAD system was used to help suggest areas to look at, and based on that, the system itself was quite poor performing. But because of the suggestions given, there was either overtrust or undertrust. Things were missed that were detected by it, or people went to the wrong area of the image and kind of, yes, I don't see anything where, maybe this is something that is malignant, but actually turned out to be just an artifact that wasn't kind of important. So if these systems aren't posed correctly, and that's why I think we see a very slow acceptance of these, obviously for a number of regulatory reasons, but if these systems aren't constructed correctly, it's very easy for them to be detrimental in a clinical setting and there to be no benefit from them.
No, indeed. No, I completely agree with all the points you made there. And on that, with the explainability models that you are working with or have come into contact with, how reliable is that? Like when a, maybe either in your own research or in like what is state of the art at the moment, because I have seen that the FDA has approved various computer vision tools for medical imaging. I think one of the more notable ones was around fundoscopy, the back of the eye. I'm not sure if they had explainability built into that, but how reliable are those systems today? And if they're not reliable enough yet, like what do you think still needs to happen, or how far are we from having them be reliable enough?
So in terms of the underlying techniques that are used, I stand to be corrected, but there haven't been any definitive techniques that have shown to be completely foolproof. Like heart attention models, for example, part of the reason why that they're being researched and that they're being considered still is even in our research, they are very error prone. So the sort of explanations that they'll derive are susceptible. So at least you can see explicitly where it's going wrong, but the intuition behind why why the explanations are being provided and their utility is questionable. Going on to what you're saying about fundoscopy and things being accepted by the FDA, in my knowledge, those systems are often accepted not because they have, very sophisticated explainability methods. They've just in the given domain been battle tested extremely rigorously. And so it's in saying, instead of emphasizing explainability for the system, we're going to have widespread, populations that are used, studies that are used. And so we're going to battle test the system to know that it functions to a certain level of performance. And I suppose there's analogies to that within medicine where we don't always understand the mechanism of a drug being used before it's accepted. It just needs to be validated really well in like several random controlled trials essentially. So there's still this uncertainty that exists, and so I think explainability, if we're using a machine learning system effectively, becomes extremely powerful. But some of the systems that are going through, I think more so are going for a route of they're extremely battle hardened, battle tested for a very niche application and not a wide ranging sort of thing. So the complexity is very much narrowed down, and we make sure as anything that we battle tested on sufficient data and diversity of data in order to derive the we know that this thing is working correctly.
Thanks. Yeah, no, I mean, I'm very tempted to delve down the explainability versus interpretability in healthcare, because as you mentioned, we don't know how some drugs work. We just know that they do work, and we can show that there is a causal connection there. So that is sufficient, or has been used in healthcare for a long time. But I'm not going to go too deep into that because we're already running. It's already 20 past 7 here, so I know our cutoff is sort of at like 1/2 past, but we can hang around for as long as people might like to. Although I don't anticipate it'll be too much longer. So let's, if there are any questions from anyone in the audience, you can either please ask in the chat if you'd like me to read it out for you, or you're more than welcome to either raise your hand with the reactions emojis and we can call on you, or you can just unmute your microphone, because this is fairly informal and there are only a couple of us at the moment. So I'd encourage anyone from either a machine learning or a healthcare background to ask questions, because especially from healthcare backgrounds, I'd like to hear what people might be curious about when it comes to these kind of techniques, because at the end of the day, it's you all that will be making the diagnoses at the end of the day. Do we have any questions? None that I can see. Let's put it this way. Jonathan, do you have any questions for any for us actually, like let's say the Sasonke Bartek community, while we have you here?
I would love to. I'm going to segue quickly to Tim, who's saying, they could be applied to medical images that could have noise. How susceptible are they to more noise themselves within images? And I think that's a very good question. So, one of the recent papers, it was a 2019 paper in NeurIPS, where hard attention was being restudied. One of the hypotheses they were trying to prove that, at that time, there was a lot of interest around adversarial attacks being done on images. Basically, obviously you perturb a given image and it's going to produce a different classification output. And the theory was, well, it's very difficult to do that for a hard attention model because we never have the entire image being processed by the model itself. It is looking for what, the underlying mechanism, what we think is happening in a hard attention model is it's looking for salient pieces of information, a subset of the image. And so, it should be robust against adversarial attacks in the sense that it's looking at different portions, a subset, not the entire thing. And so it's not a gradient pattern that's going to be applied to an entire image to make it robust. And the interesting finding that came out was that no, unfortunately, you could game a hard attention model as well. So, the researchers were trying to consider different ways around that. But the unfortunate thing is at the current stage, hard attention models are susceptible to adversarial attacks. And if you think of this, input image, if there is a high enough amount of noise, as we can currently see in our study, a hard attention model would be susceptible to that. And that then requires, us to do more things like image augmentation, exposing it maybe to some more speckle noise and stuff like that. But the main thing that we're trying to look beyond is saying, let's not just rely upon a hard attention model, because as I say, it can be susceptible to noise. But if we are extracting, appropriate pieces of, appropriate concepts from the image, then it becomes a lot more robust to something. Because if it can find a concept and extract it, then we have that embedded and we can see reasoning over that. So the system might fall over where it isn't able to extract the right concept because it hasn't found it due to noise. And there we have to look at underlying computer vision techniques to being a bit more robust to adversarial processes, being robust to noise in that sense.
Thanks. Sorry, Tom, I missed that question there. Are there any other questions? I'm going to sort of just leave a little bit of silence to give people a moment if they'd like to ask. Cool. I take that as no further questions on that. So then I will just put one final question to you, Jonathan, and then we'll sort of call it a day. I will after that also just hang around if anyone wants to just chat more generally, or if anyone's interested in getting involved in Sasonke. But yeah, so my last question then, Jonathan, is because our community has a focus around machine learning in Africa for healthcare. I mean, it's first of all just great to see African or researchers working on essentially computer vision research that is applicable worldwide. But in an African context, what would you think is like the importance of this? Is there, I mean, as an example, I think having more machine learning in primary healthcare in African context is very useful, because it helps lighten the load when we have reliable tools to let's say, take the work of maybe 10 radiologists and allow that to be done by sort of five individuals. What do you think? And then James, I see your hands up there. I'll hear your question after Jonathan's. Go ahead. Sorry, go ahead.
Cool. Yeah, I think I appreciate the framing of the question. So, as mentioned, this research is more so general. You know, it's not specific to medical imaging only, but I do have a soft spot for it, and hence the talk was kind of steered towards that context. My master's was, you know, in reading chest radiographs using deep learning. It was in medical imaging, and I think, you know, I felt quite passionate about the fact that, you know, definitely we aren't going to have anything that is automated, but being even applies as said in like a more so screening context. I think there's a great need for that. I think there's a bit of cynicism from my side. You know, you showed that pyramid right at the start in terms of the actual hierarchy of needs for like sophisticated machine learning to be deployed. I mean, you have quite a lot of individuals who you know, want to be active in the space. I think it's you know, there's so much we can do, but at the same time we you know, like, you need a good good internet connection or a decent mobile device in a remote area in order to use this technology. So while I think this is applicable, I mean, we're still limited at a low ground, and that's one thing to discuss. The other thing that, you know, really got me when I started my research in my master's was the fact that you know, there was multiple studies done by a guy, Bram van Ginningen, who's very famous in this area for radiographs and studying them. But essentially, he had a CAD for TB program that he set up, and several African countries used it. And it was just sad in the sense that what would happen in these centers is anyone who had a computer would take a radiograph, digitize it, and then send it off to the Netherlands for $25, which was quite an exorbitant amount for a single radiograph, and they'd send it back with a diagnosis. And the underlying models, you know, if you got into the literature, was very simple. So, I mean, I don't think we have a very rigorous process, and this is more for the community to speak about and to reflect on. I don't know what our process is of accepting, you know, if we were to have a system, you know, that is very performant come about, you know, I don't know what the process is of, you know, how readily that would be solved, how readily it could be utilized. But it is sad that, you know, we once again are looking outward to have, you know, very simple systems just doing screening, and that's coming from, you know, the you know, it's certain parts of Europe and the first world, and we aren't generating more of our own solutions. So I do feel quite passionate about saying, like, I think, you know, it's something like just being able to, it doesn't have to be a fantastic tool, but something that can do radiograph screenings, that is very applicable in our local context. But perhaps there isn't more of a you know, a clear way of how to innovate in this space, and it's probably at forums like this that you know, communication needs to take place, or like, how does it go forward, how does it go further? James, sorry, you had a question.
Yeah, thanks so much for the presentation, by the way, guys. So I come from a medical background predominantly, and my sort of level of understanding of machine learning and AI is incredibly basic. So a lot of this unfortunately went over my head, but still very interesting. But I was kind of just thinking now, more a thought than a question. But when Tim mentioned trying to apply these sort of hard attention models where there could sort of be noise in these medical images, maybe like a sort of entry point for this technology would be to start off with saying, whatever sort of radiographic or radiological image is taken, it can at least determine immediately whether or not there is too much noise to be interpreted by a radiologist or a different kind of doctor. And then sort of moving on from that, you could have a sort of standardized level of imaging that happens then, and that'll make it a lot easier to kind of like develop this technology once that's in place. Because I know like a lot of the time, I mean, at least in my experience, what seems to occur, especially in primary health facilities that have access to radiographic machinery, you do often get images which you can't really interpret anything from them because of the noise or the overexposure or whatever it happens to be. And that's a problem on the radiographer sort of level. So maybe one of the entry points of this technology in the beginning could be sort of trying to solve that problem.
I mean, absolutely agree with that, and I think, you know, for the wider room to reflect on as well, you know, once again it strikes me that when we have this hierarchy of needs, you know, I know in certain places, I don't know if the institutions that you've worked at, sorry James, just in terms of context, but I mean, I don't know if, you know, all our, you know, I know, for example, because my wife's in Borough, you know, you can have digital radiographs, but you have no form of a PAC system anyway to kind of just like pull everything together. Like we're missing fundamental pieces of technology. I absolutely agree that it's like, you'll probably find it's something that is a lot simpler, that will have far more impact, and it may save you time of, you know, sending a patient to have a radiograph, comes back, it's uninterpretable, you have to send them out again, and that's a slog with porters and, you know, arranging something like that. It'll save you a lot of time just as a practitioner, being able to have, you know, as the radiograph is taken, saying, is this the correct orientation, you know, is the exposure correct on this, instead of, you know, doing it again. So I completely agree, and so the moral there, I suppose, is, you know, we don't have to do a lot to get things right. And I think, Chris, I don't know if you've shared the story before, but or how it's gone, but a while ago, Chris was brought into a project in the rail lab, which was basically, you know, being able to take a pathology slide, you know, it was hematology, essentially looking at blood smears. And sorry, you have to correct me at any point, Chris, if I'm erring incorrectly, but, you know, it was simply being able to digitize a given slide, maybe detect something relevant in it, but just digitizing the slide so it can be made available to an expert who maybe is not on site in order to do this reading. And that would have saved lives, you know, like it's something simple like that. So we can speak about the, you know, like the advanced machine learning aspects, but sometimes it's a simple intervention like that that will have the most, you know, impact, or can have impact over and above like intelligence that we're adding.
Yes, Jonathan, just to add to that story, yeah, very often when people talk about, let's use machine learning on this or that, and often I think we hear from government agencies getting very excited about the fourth industrial revolution, and we should do 4IR. And it's like, well, before we can do 4IR, we should probably try 3IR. And yeah, let's start there. And I think, yeah, you're completely right. Just trying to like digitize hospital records. I mean, the fact that in at least a South African context, we have a lot of stuff that is still paper-based, you know, makes that very hard. And on that, digitizing the hematology slides, one of the things that was happening there is there would be a technician with a slide on the phone to a hematologist, and they would be doing like a telemedicine situation where the technician would be moving the slide around so the hematologist can look at it from wherever they are. And, you know, even that is you know, a step up, because that allowed very rapid diagnosis of I think it was severe like leukemias that needed to be addressed within you know, the space of like 24 hours or 48 hours. So yeah, I think that we really do need to build our fundamental foundations of just collecting the data and digitizing. I mean, there is a really cool thing that our government did, South African government that is, where it is a policy that exists, and I can direct individuals on our Discord channel to where it is, where unless otherwise shown, like our government should be using like open source data, not data, software to implement systems. And I'm not entirely sure how often we actually use open source systems to in the public healthcare system, because I know, like, for instance, our national pathology labs use rather expensive third-party tools all the time, and it kind of begs the question then, why don't we have a national or public open source electronic health record system that is sponsored by like tax, for instance? Like that to me, you could even like have a couple countries put their tax towards a context relevant electronic healthcare record system, and that would provide way more benefits than all of the machine learning stuff that we tend to dabble with. So yeah, I agree.
I mean, I think it's the life chain of hospitals. They're only undertaking now to have fully digital records, right? Speaking to a colleague of my wife's the other day. So I mean, we are not progressive even from the private side.
Cool. So we are sort of just over time. I'm going to give us an opportunity to say thanks again to our speaker this evening, Jonathan. Thanks. It was really great having you here. It's your first talk with Sasonke Biotek. I hope it's not going to be the last. I would also encourage anyone here, if they at any point would like to give a talk, you're more than welcome to just reach out to us. We got one more point in the comments. Cool. And
it's just a thanks.
Yeah. So we'll be having another monthly meeting like this, probably next in January. You'll hear announcements via the mailing list. If you haven't signed up for it already, just go onto our website. That's sasonkebiotech.africa. If you want to get involved in any of our projects, just hang on after this. I'll be hanging around to chat. This has been fun. Thanks again.
Awesome.
And I'm just gonna stop the recording and we can call it an evening.